Welcome to the Kentucky Watershed Academy. This is Module 4, dealing with data, and in this presentation we're going to be looking at basic statistics, graphs, and charts. We've all heard the funny quotes about statistics, and we laugh because there is truth behind them. As a watershed coordinator, your goal is to faithfully communicate the data to others. You serve as a trust agent working between the technical consultants and the decision makers and stakeholders. Your job is to faithfully explain what the data indicates. That means that you will have to do your best to avoid misrepresenting or misinterpreting the data. A full analysis of water statistics and visualization would likely be a week-long course, and our goal in this section is just to hit on the high points. During this presentation, we're going to look at some basic descriptive statistics, different ways to visualize data through charts and graphs, and some pitfalls of those methods. We'll look at different benchmarks for comparing the data, and look at report cards and multimetric summaries in order to simplify for non-technical audiences. And what will likely be most people's least favorite portion of this presentation, we're going to start off with some basic statistics. We'll begin with measures of central tendency. Often we will use the term average, and when we use that term in our conversation, we're typically referring to the arithmetic mean. You sum all the numbers together and divide by the count of the numbers. The only problem with this measurement is it tends to be biased towards the higher numbers. Therefore, it is often not the best way to measure central tendency in environmental data sets. There are other ways to measure central tendency that may better represent the data. The geometric mean and the median are two of those. Geometric means are typically better for representing environmental data because they are not as skewed towards high values. However, they cannot be calculated with zero values, that is, non-text must be substituted with a low value. Medians are another common method for calculating the central tendency. All values are sorted from least to greatest, and the middle number is the median. 50% of the results are above and below this point. Excel functions for these different ways of calculating the central tendency are indicated. This will be used throughout. You would put in the range of cells between the parentheses to be averaged or to find the central tendencies using these various equations. This is a visual representation of how several different measures of central tendency compare using a few different data sets. Now, the black boxes are for the arithmetic mean, and they are the highest in each instance. The median is the blue line, and the geometric mean is the red circle. Which one is correct? Well, you'd have to ask a statistician for that, but the geometric mean or the median tends to be a better indicator with the environmental data. Skewness is the measure of symmetry of probability distribution around a mean. In a normal or a bell-shaped probability, the one shown in the middle, both sides are equal, so there is no skew. The mean, the median, and the mode are all the same. A general rule of thumb is that skewness indicates the direction of the longer tail. So left skew is negative, right is positive. Another way to view this is that the direction of the mean as compared to the median. However, these rules can fail if you're dealing with some multimodal distributions, more than one peak. That's going to be beyond most of our purposes. This can be used along with a histogram to show, for instance, whether a confidence interval can correctly be applied to the data set or not. Another basic statistic is a measure of the spread. There are a lot of different measures, and we'll just cover three of those. One is a range. This is simply the difference between the maximum and the minimum values. That's the range of the values. Variance and standard deviation are two related measures of spread. The standard deviation is simply the square root of the variance. For example, for the numbers 1, 2, 3, and 4, the mean is 2.5 and the sample variance is 1.67. The standard deviation will be 1.29. Now, the standard deviation is helpful because it provides some information of if a normal or bell-curved distribution is present. This illustrates what a standard deviation shows. You can see that 68% of the results are within one standard deviation of the mean, and 95% of the results are within two standard deviations of the mean. Now, there are statistical tests that can be used to calculate 95% confidence intervals and such, but that's a deeper dive than we can get into in this presentation. We will look at one other way to summarize the spread of the results, and that will be quartiles. Quartiles are a way to measure the spread and combine some of the elements we've already talked about. How many quarts are in a gallon? 4. So likewise, quartiles are a way to divide up the data into 4 equal groups, starting with the minimum, that's the 0 quartile. The first quartile is from 0 to 25% of the results, and then from 25% to 50%, that is the median, and then the median to 75% of the results, and then 75% to the maximum, that's the fourth quartile. This provides a very nice summary of the range of the data and the central tendency. It can also be very helpful in performing outlier screening. Potential outliers include values that are 1.5 times the interquartile range, or the middle 50% of their values. This may be better illustrated in the following graphic. This graph is called a box plot, or a box and whiskers plot. You look first at the median. That's the line in the middle. 50% of the values are above and 50% are below that value. Now we note the maximum and the minimum. These are the lines. Some box plots do not have the outliers as dots, but go all the way to the maximum and minimum. The whiskers extend all the way out, if you will. The interquartile range is the box portion of the graph. The middle 50% of the results are within that box. That is the interquartile range. In this graph, the potential outliers were identified by multiplying the interquartile range, that is the box, by 1.5 and adding or subtracting to the bounds of the interquartile. Potential outliers should not be excluded from the data immediately. In fact, they may be the most significant finding in the dataset. Rather, they should be investigated to see if there's a typo, some sort of lab error, or something out of the ordinary occurred during the collection. For instance, if it was a storm event or a very turbid data that was collected. Outliers should only be excluded if they are suspected to be in error. We'll have one last stats-related slide here, and then we'll be done. Whew. Unless someone did a calculation of statistical significance, you need it to be careful about drawing too many conclusions because one number is bigger than another. A large difference does not equal a statistical difference. The chart indicates a random sampling of a known data set at a 95% confidence interval. All of these results were obtained by sampling the same data set. So one sample, another sample, another sample, different results from the same set of data. The dots, that is the dotted red line, is the true mean of the entire population. The blue dots are the means based on the sampling, with the lines representing the 95% confidence interval. As you can see, two of the sampled sets, those that are marked with the red horizontal lines, do not contain the true mean at all in the data set. In fact, it would be expected that 5 out of every 100 samplings of the true dataset would not contain the true mean. It is important to understand, and many people do not, that confidence intervals are not error rates, just the portion of random samples that contain the mean. If you'd like to see this illustrated in real time, the website link located on the slide will generate these sampling intervals again and again, so you can kind of get the overall concept. And if you really want to dig deeper on your stats, there are some great guidance documents that are out there that can help you explore more fully. Here's two, one from USGS and the other from the EPA. Okay, stats are great, but if you torture them, they'll tell you anything, right? And to illustrate that, you need more than just statistics to tell your story. Here's some rather dry statistical data for X and Y coordinates, with a mean and standard deviation, as well as a correlation coefficient. So, based on this information, what does this plot look like in your mind? Well, it turns out that that plot can look like a lot of things. All of these images have exactly the same summary statistics. So you could see, telling the story of the data requires more than just statistics. You will need some sort of data visualization. Now, likely your data will not plot out in these manners, but you need to think, what sort of visualization should you use? The website datatoviz.com has some excellent details on how to select the right data visualizations for your particular project. We're going to explore some of the more common visualizations and some of their pitfalls based on this website. We want to begin with the pie chart, which is a very commonly used chart. We'll compare 3 different pie charts. How do you see the relationship between these 3 pie charts? What kind of trends can you gather? Now look again. This is the same information shown on a bar chart. Can you see trends now? What does this tell us about pie charts? Well, it tells us that generally we should avoid using pie charts. Our eyeballs just don't do a good job of picking up the differences between these portions of a pie as opposed to a bar plot or some other alternative. Especially if you're going to use a pie chart, do not do a 3D or exploded pie chart. This just unnecessarily complicates the visualization. Next, let's consider bar plots. We have 2 bar plot maps with the same data sets. Notice the difference between the top and the bottom with the color choices. What do you gain from the top map versus the bottom? Are you trying to tease out what the different colors mean? They don't mean anything. It unnecessarily complicates the data set. If you're using a bar plot, which are very good to have values from independent categories, make sure that you do something that these have done nicely, which is ordering the bars according to their value. This allows for comparison. You can see very clearly United States is much larger than Russia, and you can begin to see how similar Norway and Switzerland are, for example. But don't add color if it doesn't add meaning. And if you have long labels, use a horizontal bar plot as opposed to a vertical one. When using a bar plot, be careful with using error bars. It's difficult for people that are reading the graph to understand. Is that a standard deviation? Is it a standard error? Or is it a confidence interval? So avoid error bars is possible, but if you need them, consider a box plot or label them very clearly in a note underneath the chart. Histograms are a great way to summarize the distribution of results. It doesn't show the exact results, but it shows the number within a given category. Of course, what's critical in this type of summary is the size of the categories. In this case, the histogram on the top has a category that's too large, whereas the one at the bottom, this is the same data, is refined, and so you can actually see a better representation of what's going on with the data set. So histograms are for summaries of the distribution, not for indicating precise values. And make sure that you adjust that bin size to tell the story. And make sure bin sizes are constant across the board. You don't want to have one bin is a small number and one is very large. Our eyes say that these should all be consistent sizes. We've talked a little bit about the utility of using a box plot to summarize the distribution of data. There's a lot of information that's provided here. You get the mean, you get the max, you get the min, you get that interquartile range. But it's important to realize that some data is actually hidden. So on the top we have the box plot, and in the bottom we have a violin chart where the width shows the number of results that are in a given range. So you can see some information on the distribution is hidden. For instance, look at the blue. You have a bimodal distribution there centered around the interquartile range, but you don't detect that in the results. You also can't tell how many results are being summarized. So A has 500, B 1,000, C 20, and D 100. So it's important if you have differences in sample size that you indicate that data at the bottom of the chart. This chart is an example from the City of Lexington's annual monitoring program in which chemical data is normalized by dividing by the benchmark. So the benchmark is the red line across the bottom. The yellow dot is the median in each case, and then of course the blue is the interquartile range. So in this case, you can see the number of times higher than the benchmark that the data is located. This allows you to very quickly see that conductivity is a problem, total dissolved solids is an issue, E. coli and fecal coliform, total phosphorus, and total nitrogen need to be addressed. So this is one chart that summarizes a whole lot of information. A scatter plot is a great way to show the relationship between two different variables. It's also a great way to identify groups or trends. You have to be careful that if you have a whole lot of data that you don't overplot, and so you get a big clump of dots that you can't discern one from another. And if you're using a time series, so something that occurs over time, you might want to use a line plot or connect the dots. We want to note that in this case, both axes are shown in a logarithmic scale. A logarithmic scale is used to show data sets that occur over a very large range. And so rather than counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, it counts in 10, 20, 30, and so on, and then 100, 200, 300, and then 1,000, 2,000, 3,000. So be careful to check the scale on your charts and graphs. The next graphic we want to look at is an area plot. An area plot is great looking at changes in variables, typically over time. But be careful with stacked area charts. These are useful for showing a lot of data, but they can be difficult to estimate some areas if you have a lot of changes in given data set. For instance, look at the utility of having a grid of area plots, takes up the same amount of space, as opposed to, I mean, did you really get the differences in these different periods here? Some of these small changes. Be careful of have too many lines in a stacked data chart, and so a grid of small charts may be more useful instead. Rather than using charts, you may consider using maps to display your data. Choropleth maps are ways to display the values for regions of an area. So you can see, as an example, counties are being used to show the fecal coliform concentration in a given range within that county. The top map does a great job. It doesn't use a continuous scale, but it breaks it up into different bins. We have trouble recognizing a continuous scale and finding the value on that. So you want to use a few set distinct colors along the way. But be careful. You can see, for instance, Pulaski County, you're seeing a large dark red spot, but it's only being represented by very few sampling points. So the size of your region can bias the way that that map looks. And that in that case, you may consider using a dot map or something like that. An alternative is a bubble map. Bubble maps take data at points or regions, and they use either the bubble size or color to show the magnitude of the concentration, for instance, or as the top map shows, this is the average discharge range of wastewater treatment plants. So you can see the size of the dot indicates the amount of the discharge. But you can use the color the same way. This can help address some of the bias of a Choropleth map, but be careful of having too much data. When you're trying to determine what sort of visualization to use with your data, there's some general recommendations that will hold basically across the board. One, avoid using dual axes. While this may be useful for highly technical reports, it can be misleading and hard to read. And so instead, you should use side-by-side charts or some other alternative. We'd also recommend that you highlight the important parts. Don't make people try to figure out the main point. Label it or otherwise highlight it within the graphic itself. Make your visualizations stand alone. It doesn't need to be interpreted. Notes can be included, but that should all the information you need to interpret your visualization should be contained within the visualization itself. Okay, next let's turn our attention to data and some different benchmarks. We want to look at some tricky comparisons that often come up for watershed coordinators and ways to compare different methods to make comparisons. First, we want to look at the bacteria criterion. The primary contact recreational period for E. coli has two different types of criteria. One is based on the geometric mean, and the other one is a not to exceed in 20% of the samples. The same holds true for the secondary contact recreation for fecal coliform. So here we have some summary statistics from E. coli based on results of 5 samples in May taking at 3 sites. So which of these sites is worse, A, B, or C? Here you're looking at the percent that's exceeding 130 mpn per 100 milliliters. So it appears that site A is the worst, correct? What about now? This is the percent exceeding 240. Well, now you can see site A never exceeded that amount. Site B, about the same amount, and site C, 60%. So which one's worse? So you can see if you have the geometric mean, site A and site B are pretty similar, but they're just close to that value. Site C is a lot higher, but the summary statistics were hiding some of that data. You can see these are the results that are behind it. So you have a geometric mean 131, but because all the results were just slightly above that 130 criterion, you get a whole lot that's slightly exceeding. But if you look at the reduction to meet the value, you can get some more information. Okay, so all these different sites are impaired, but for different reasons. So you can see sites A and B are both impaired for exceeding the geometric mean. You can see sites B and C are impaired for exceeding in 20% of the samples that 240 threshold. So you need to be careful about only showing frequency, exceedance, or magnitude because these are summary statistics and they can be misleading. You may need to use several different statistics in order to really paint the right picture. Another tricky benchmark shows up in 401 KAR 1031, and you'll see these long equations. For example, we can see here the warm water aquatic habitat acute criteria from cadmium has this E number and LN hard asterisk. What does all of this mean? That metals criteria, that's written in the regulations is actually an equation. And you can see in the red is how you would translate that equation into Excel. Column A is where you have the actual cadmium result. Column B in the green is what the hardness value is. And then you could type in that equation in column C and it will calculate this out. There's the criteria. And in column D, you can actually write an if-then equation that'll tell you if the criteria was exceeded or not. Similarly, the unionized ammonia criteria has a long, complicated equation. You know it's supposed to be not greater than 0.05 milligrams per liter, but how do you calculate the unionized ammonia? You can see here the equation shown in column D utilizes the ammonia concentration, the pH, and the temperature in the various columns. So you can copy and paste this equation and drag it down in the column in order to compare with the criteria. You can see in this case the same ammonia values, same ammonia concentrations at different pHs and temperature can result in one being exceedance and the other not. We talked about the difficulty of telling the story of E. coli data, that is, showing the magnitude and the percent exceedance of these values. This is one way in which you can communicate that data. So here we have the E. coli and the two different criteria, SCR being for secondary contact, PCR being for primary contact. And you can see the percent exceedance of each of those values by site. These are also color coded, and the color coding is shown also with the geometric mean concentrations. Um, in this case, the bottom graph shows those geometric means underlining the site if the geometric mean exceeds the threshold. So using these in conjunction, you can pretty quickly see what are some of the sites with the largest impacts. Here's a similar example of the same type of approach, but for iron in this case. So we have a drinking water supply standard, a chronic threshold, as well as an acute threshold. And you can see the percent exceedance and the concentration. And this enables you to see how different uses are impacted based on the same data set. Developing a report card or a multimetric summary may be useful if you're communicating with non-technical audiences. The National Water Quality Monitoring Council has an excellent fact sheet that talks about different types of ways in which you can accomplish this. An excellent example of a report card approach is the Division of Water's TMDL health reports. In this report, each parameter is provided a grade, A, B, C, D, or F. This is something that we're used to. We've gotten grades in school, and so they've translated over that water quality data into an easily determined grade. The general process in creating a report card is to select key health variables, then establish breakpoints. These can be either regulatory criteria or scientific benchmarks. And you can either assign 3 of those, so you can have a good, fair, and a poor, or you can have 5 different breakpoints, so you can have that traditional grading scale. Or sometimes people will use a scale from 1 to 100. And this can be done based on frequency of exceedance. It can be the magnitude of the concentration or the load. You have to look at what's going to best convey your focus area information. And then you're going to allocate this to an area, a stream, or a point. Here's an example from the Chesapeake Bay report card. They've taken a lot of variables, listed over to the right, and summarized them into an overall Bay health indicator. This allows for a very quick visual summary based on a scale from green, good, red, bad, for someone to see at a glance where are the impacts occurring. A local example of this approach is shown here in human health grades for the Chestnut Creek Watershed Plan. So this is based on a percent exceedance circumstance uh, for E. coli, and this allows you to very quickly summarize where does the load need to be reduced, what is currently meeting the regulatory limits, and this captures information. For instance, those red stars are locations with failing sanitary sewer facilities, and the areas marked with a D have a lot of agricultural setting there that would need to be fenced out. So a quick summary information for what are causing the impacts and where to focus attention. So again, the goal is to distill large data sets into the easily understandable visuals that are actionable by decision makers. You have to be aware of your own data's limitations. And your goal in communicating is you want it to be not just possible to understand, but impossible to misunderstand. That's part of your job as a communicator of the data. And we hope this overview of some different options, pitfalls, and considerations will be helpful in determining your best data visualization needs.